In this lesson, we're going to be looking at the idea of hybridization as it relates to VSEPR theory, valence shell electron pair repulsion theory. So we're going to be blending atomic orbitals to make hybrids, and as we're doing so, one thing I'd like for you to notice is that the number of atomic orbitals that you put in equals the number of hybrid orbitals that you're going to get out. And every time we make hybrid orbitals, we're going to then look at the electronic geometry associated with each type of hybrid. So let's say that we need two areas of high electron density around a central atom. That would actually call for sp hybrids. So if you have two areas, let's take a look at sp hybrids. To create two areas of high electron density, you must take one s orbital and one p orbital and blend them together to make two sp hybrids. Notice that the sp hybrids are 180 degrees apart from each other, and this would be called a linear type structure. So whenever you want two areas of high electron density, you're going to blend an s and a p orbital, making two hybrid sp orbitals that are 180 degrees apart from each other. If we would like three areas of high electron density around a central atom, then you're going to need sp2 hybrids. And as you see in front of you, this would be called a trigonal planar arrangement, and the bond angles between these hybrids would be 120 degrees. So what does it take to actually make sp2 hybrids? You have to put in three atomic orbitals to be able to make these three hybrid orbitals. So let's take a look at how we're going to make sp2 hybrids. In making sp2 hybrids, you take one s orbital and two p orbitals, and then you hybridize them together, and upon hybridization you get three equivalent sp2 hybrid orbitals. The electronic geometry for three areas of high electron density once again will be the trigonal planar arrangement, bond angles 120 degrees. If a central atom has four areas of high electron density around a central atom, this would call for sp3 hybrids. So four areas around a central atom, the geometry would be tetrahedral, and the bond angles would be 109.5 degrees. Now to make these four equivalent hybrid orbitals, we're going to have to put in four atomic orbitals. So let's take a look at the atomic orbitals that have to be blended, mixed together to make the sp3 hybrids. So the mixing of one s orbital and three p orbitals is going to allow you to make four equivalent sp3 hybrids. These sp3 hybrids will have a tetrahedral arrangement with bond angles at 109.5 degrees. If a central atom has five areas of high electron density around a central atom, then we have to be able to explain the electronic geometry. In this case, that would be trigonal bipyramidal. You're going to see that there are three hybrids within the plane. They're actually 120 degrees apart from each other, and then two of the hybrid orbitals will be above and below that plane, obviously at 90 degrees. So how are we going to make sp3d hybrids? Well, you're going to have to put in five atomic orbitals to make these equivalent five hybrid orbitals you see in front of you, these sp3d hybrids. So let's actually put in the five atomic orbitals that are going to be needed. That's going to be an s, the sphere, all the dumbbells, three of those, but we're also going to have to take advantage of one of our d orbitals to allow us to put in five atomic orbitals. So let's take a look at this. So the blending of one s orbital, three p orbitals, and one d orbital is going to give us the equivalent five sp3d hybrids. So once again, you have to put in one s orbital, three p orbitals, and one d orbital. Let's make sure we see that again. It's one s orbital, three p orbitals, and one d orbital to make the five equivalent sp3d hybrids. What is the arrangement so that you can have five orbitals around a central atom? Well, three within a plane, 120 degrees apart, and then two above and below that plane at 90 degrees. So this would be your trigonal bipyramidal arrangement. This is for five areas of high electron density around a central atom. If you have a molecule that has 6 areas of high electron density around the central atom, that is going to require an octahedral arrangement, and all the bond angles here are 90. You have 4 of the hybrids within a plane, and they're 90 degrees apart from each other, and then 2 above and below this plane that also are at 90 degrees. To make 6 hybrid orbitals, you're going to have to put in 6 atomic orbitals. So we're going to see that you're going to have to put in one of the spheres, the S, all 3 of the dumbbells, and 2 of the 5 d orbitals to make 6 equivalent sp3 d2 hybrids. So let's take a look at the atomic orbitals that have to go in to actually make the hybrid orbitals you see in front of you. So mixing an s orbital with 3 p orbitals and 2 d orbitals is going to give you 6 equivalent sp3 d2 hybrids. So mixing an s orbital with 3 p orbitals and 2 d orbitals is going to give you 6 equivalent sp3 d2 hybrid orbitals. What is the final electronic geometry for this type of structure for 6 hybrid orbitals? It's going to be the octahedral arrangement, and obviously the bond angles within the plane and above and below the plane are 90 degrees. And this is for when you have a molecule that has 6 areas of high electron density around that central atom. In summary, if you need to make hybrid orbitals, the number of hybrid orbitals you can make is based on the number of atomic orbitals you put in. So if you need 2 areas of high electron density, linear, 180, you're going to have to put in an s and a p orbital and make 2 hybrid sp hybrid orbitals. If you need 3 areas of high electron density, you're going to have to put in 3 atomic orbitals. You're going to have to put in the s and 2 p orbitals and make 3 equivalent sp2 hybrids. 4 areas, you're going to need to put in an s and 3 p orbitals, and upon doing so you'll make 4 equivalent sp3 hybrids, which is your tetrahedral arrangement. 5 areas requires 5 atomic orbitals, the s, 3 p orbitals, and a d orbital, and blending them together will make the 5 equivalent sp3d hybrid orbitals. That is your trigonal bipyramidal arrangement. Bond angles within the plane are 120 degrees, above and below the plane they are 90 degrees. And if you need 6 areas around a central atom, that would require 6 hybrid orbitals, so you'd have to put in 6 atomic orbitals. That would be an s, 3 p orbitals, and 2 d orbitals to get the 6 equivalent sp3 d2 hybrid orbitals. What is going to be the electronic geometry? It's going to be octahedral. Bond angles are going to be 90 degrees in the plane and 90 degrees above and below the plane. So what you see in front of you is a good summary of how many areas of high electron density you can have around a central atom, what the electronic geometries are going to be, and the corresponding bond angles.